Hi everyone, this is the second half of the lecture on implantable microelectrode arrays for Parkinson. Until now what we have seen? We have seen how to what is Parkinson, what happens when there is a freezing of gate, what are the regions in which the neurosurgeon will implant the electrodes, and what can be an alternative region which people are working on, and our effort on our efforts on using the surface plus deep brain to see whether it will improve the current treatment of Parkinson, right. So, for that we need to work on animal model, and for that we have discussed about rat or rodents in detail. Now, let us understand the design and surface of the neural implant. So, in the last slide, if you remember, right, what we have shown is we have shown that what are the downside of the commercial available implants, and we have also shown that what are the areas which are of our interest, and in particular how we can fabricate the device. So, let us understand how we can fabricate this particular device. So, if you see this particular image, right, in this image again our interest is of 3 mm by 8 mm, that is the area that we are interested in. And what else we are interested in? We are interested in the device that can be implanted in this particular region. So, for that we need to fabricate this device, and this device can be fabricated if you know how the microfabrication technology can be utilized or can be used. So, in this slide what you are able to see is the image where we want to implant the device, right, and here on the right side you are looking at the design of the surface neural implant. Now, we have talked about the deep neural implant and surface neural implant. This is for the cortical surface stimulation and recording. If you see this design, right, there are 5 electrodes, 1, 2, 3, 4 and 5, and each electrode is about 400 micron in diameter, and the if you see the length, right, is 3.9, which should fit somewhere in this area like this. It will fit like this, okay. And then you have another device that will go in this area like this, alright. So, that is why we have designed this with this angle, so that it can fit well in the brain. Now, you can also see the wavy structures here like this, right. The reason of that is to reduce the stress when the device is stretched. So, it is a flexible device. I have told about the advantage of flexible device, that it will damage the tissue less compared to the hard devices which are made up of silicon. So, the substrate thickness in this particular case, which is the polyimide, is about 20 microns. As I told you, the substrate material is polyimide. The electrode, which is the recording electrode, right, and this one, right, including the connecting lines, are made up of titanium and gold, and this and then on that we can also use conductive polymer like P.PSS, right. We have seen why P.PSS is important, right. And then now if you remember, right, P.PSS, then I have shown it to you that the P.PSS has certain advantage over the gold and platinum, that it will improve the charge injection limit. It will improve the charge injection limit. So, it is better in terms of the electrical stimulation. Now, the interconnect line width, that is this wavy line that you see, right, the line width of this is about 25 microns. The electrode diameter we already talked about, which is 400 microns, and the thickness of the titanium over gold, so below gold, right, gold is over titanium. Titanium is used to improve the adhesion of gold on the polyimide. So, the titanium thickness is about 30 nanometer and gold thickness is about 300 nanometer. So, the reason of using polyimide is that it has an excellent biocompatibility and adaptability to MEMS based fabrication process. We can use the MEMS based fabrication process, but it is deposition, which is your PVD, or it is lithography, we can easily use it. Second is that every electrode can support higher current injections when the gold electrodes are electropolymerized with P dot PSS. This is another advantage of the using the polyamide, and also the advantage of using P dot PSS over gold, because it will improve the charge injection currents or higher current injections. The next one is surface neural implant is placed on the left and right motor cortex regions of red brain for the studies, right. So, this is another advantage of a surface neural implant, that we have designed in such a way that it can be placed on left and right. So, we can change the design, or we can customize the design based on the requirement. So, that is the all about the neural implant, particularly surface neural implant. Let us understand how the fabrication is done. Okay. Again you see that a device which is placed next to the stent, to give a perspective of what is the size of the device. You can see the device on the scale, and there are 5 electrodes, as you can see here, 1, 2, 3, 4 and 5. Each side, right and left area, there are 5 electrodes that can be used to stimulate that area or record from that area. When we have this device, it is flexible in nature, that you can see from B. If you connect it with the electronic module, that you can see from C, right. You can look at the electrochemical impedance spectroscopy, which you can see from D, and then you can also see that the average impedance value is about 25.8 kilo ohms, which matches with the literature. Now let us understand how to fabricate this entire polyamide, right. So, it is a step by step. So, I will show you the each step. For here, let us see whether you all understand this step, and I will show it to you in detail, okay, in the next slide. So, first is silicon wafer. A is silicon wafer, easy. Next, B is you use the polyamic acid solution, spin coat it on the silicon, and then cure it to form the polyamide, which is PI film. The next one is that you e-beam the TiAu, titanium at the bottom, gold at the top, and then you perform the photolithography to have this design. So, let us understand how to reach to this design, and then we continue from D. Okay. To reach C, what you need to do from A to C, we will see in the next slide. Let us see. So, you have a silicon wafer, and then you can have a polyamide film, this is your PI film. Then you deposit titanium and gold, this is your titanium gold, this is PI, this one is titanium gold, right. Next step is you have polyamide, on that you have titanium gold, on there you have a photoresist. Right. Now, let us say this is a positive photoresist. Next step is you load the wafer, right, load the mask, I am sorry, load the mask, and it is a bright field mask. So, the area which has this chrome, it is a chrome mask, we have seen, right, that we can have bright field mask, we have a dark field mask, and the material that is used to pattern this mask is chrome, that is why it is also called as a chrome mask. So, this is our bright field mask. After you load the bright field mask, you know that when you spin coat photoresist, what is the next step? Next step is always a soft bake. Soft bake is done as I have told you, easy to remember, 90 degree, 1 minute on hot plate, correct. But if you have oven, it is different, right. We have seen that this 1 minute will become 40-45 minutes. Again you need to optimize this soft baked timing, okay, depending on what kind of either you are using a hot plate or using oven, depends on that. So, once you spin coat photoresist and you soft bake it, then you can load the mask and then you have to expose the photoresist through the mask using your the beauty of technology and the limitation of technology. Okay, we are back, good. So, now this is your UV. So, if you expose it through the mask, it is a positive photoresist. So, the whatever the design is there on the mask will be there on the photoresist, or the unexposed region will become stronger. This is your PI, this is TiAU, silicon, and your photoresist. You see the area which is not exposed is stronger, right. After exposing the photoresist with UV, you have to unload the mask, develop the wafer, develop the photoresist in photoresist developer. When you do that, you have this particular pattern. The same pattern that is on the mask is replicated on the photoresist because you are using a positive photoresist. After that, you have to perform the hard bake. Hard bake is done at 120 degree centigrade, 1 minute on hot plate, alright. After hard bake, the next step is you have to dip it in gold etchant, rinse it. So, first dip it in AUH etchant, then rinse, then TiH, then rinse. Okay. If you do that, you will have, I am sorry, titanium gold protected by the photoresist, correct. This is what you have. And then if I dip this wafer in acetone, then what will I have? If I dip this wafer in acetone, I will have a PI with my titanium gold, Ti with a titanium gold, correct. This is the Pi. Pi, on that we have titanium gold. So, where are we? What is this thing? This thing is our C. Now, let us see. Okay. You see here, this is where we are. Now, the next step is, if you see D, spin coating of polemic acid solution followed by curing passivation layer. So, again we have to coat the PI on the C. So, if you want to do that, let us remove all these things, and we start with the gold titanium gold on the PI, and then we coat the PI as an insulator. PI is a substrate, PI is an insulator, very interesting concept, right. Because the polyimide can also work as an insulating material, can also work as a substrate, because we can have 20 micron thickness, we can vary the thickness, it is flexible in nature, it is biocompatible. So, lot of advantage of using the polyimide in the MEA fabrication. MEA stands for microelectrode arrays, alright. So, our slate is clean, and let us start drawing again. So, we have your silicon wafer and PI and titanium gold, on that we can have one more layer of PI, one more layer of PI. Okay. So, and you know how to coat it, polymeric acid followed by curing forms the polyimide. The next step is, after this the next step is to load the wafer, to load this particular titanium gold, PI, PI, TiAu, spin coat positive photoresist, soft bake it, and then use a dark film mask, use a dark film mask, so that we can remove PI on the contact electrodes and recording electrodes. This is our dark film mask. Right, dark film mask, and then after loading dark film mask, ultraviolet light exposure. Now, dark film mask is there, and then positive photoresist is there, positive photoresist unexposed area becomes stronger. So, what we will have? We will have your PI, bottom PI, then we have these electrodes, and then we have the top PI, and photoresist. Right, the area which is not exposed becomes stronger. After this, next step is I will etch the Pi from these regions PIH. Okay. If I do that, what will I have? I will have a silicon wafer with polyamide let me just with polyamide and titanium gold very difficult to differentiate, but this is a contact, this is a contact, this is a contact and this is contact. Okay. These 4 contact regions does not have the Pi on it. So, this is your titanium gold. The remaining area has a Pi because you can etch Pi to the windows that you can see in this particular diagram. Where are we now? We are here in E. And then once it is there, we can remove this, we can strip it off the Pi from the silicon wafer to form the flexible sensor, as you can see in this one or this one or this one or even in fact this one which is connected, is not it. So, this is how the flexible sensor is fabricated with n number of electrodes. In our case, it is 5 electrodes. So, once you do that, the next step is to design the wireless biphasic pulse generator. Now, you need to understand that we are using deliberately the biphasic electrical signals because they are effective and cause the minimal damage to during the stimulation. So, you can see the anodic phase followed by a cathodic phase. The deliberately the anodic phase the time is smaller compared to the cathodic phase, and in this case the schematic of a rodent with wireless pulse generator is clearly seen. There is a 3D printed casing where there is a FPC cable interfacing PCB which is interfaced with this particular electrodes. There is a placement of surface neural implant, skull bone is there, screws are there for reference and ground, dental acrylic is there and rodent skin is there. So, this is how the electronics is connected to the brain of the rat. For details we can also understand that if you understand a bit of electronic side, then you will know that how the ECoG 5 microcontroller will work, right. You need to have a 3.6 volt battery, there is a charge pump and there is a current mirror block, there is an analog switch and then this whole thing is connected to your electrode tissue interface and also the signal that comes out is given to the open BCI and for open BCI biosensing board there is a power supply of 6 volts. So, it is a and then you can always use the LabVIEW programming for stimulation, and your graphical user face can be used with your brain computer interfacing modules. So, you want to know more about this stimulation, you can look at any of these particular references. If you do not find the references, please let me know, I will send you across. So, while doing this, right, we bought a ECoG LP microcontroller prototyping board that is easier for us to start working with, and already there are current mirror blocks and there is a HM10 BLE module for Bluetooth transmission. There is a open BCI Cyton by Daisy board which you can see here in the schematic, and the specifications that we used for this particular version where it can be real time programmable with an amplitude of 0.2 to 0.4 milliampere current. It can be wired as well as wireless control. The simultaneous stimulation of required number of channels is possible, generates constant biphasic or monophasic current pulses. It is programmable pulse frequency, pulse duration, number of pulses, duration of trail. So, all things are very easily programmable. We have validated this by performing intracortical microstimulation in rats brain at a later stage. Now, let us see the experiment. So, we have the ethical clearance and the institute biosafety clearance to perform the experiments. In this study, you can see that how the electrodes are placed in the area that we were looking at earlier in the earlier slides, right. And when you measure the signals, right, to record the baseline ECoG, then you can see that from number of channels how these ECoG signals are being recorded, right. This shows for 20 seconds recording, right, and it is on the left and right hemisphere of the anesthetized rat's brain. So, this is an actual study. We are not just talking about theory, we are not talking about just fabrication, we are not talking about simulation, but actually experimenting this particular electrode by implanting it onto the rat's brain, and this is a schematic of the same. So, when you really say about advanced neural science for engineers, this is what advanced neuroscience means, that when you fabricate a device, you should not be only able to design it or simulate it, but you should also be able to design the electronics for that, you should design these sensors for that and use it in a implant. Now, the insertion depth of 1 to 1.8 millimeter from cortical surface, this is for the when you implant a wire for electrical stimulation. So, this is the setup for providing an electrical stimulation through the biphasic generator. I will just play a video so you can see. And then let me just show you the stimulation parameters. It is about biphasic current 40 to 120 microamperes. The pulse frequency is 300 hertz, pulse on time is 200 microseconds, duration is 39 milliseconds, frequency is 1 hertz, and for 10 seconds duration done. So, when you actually see what happens is that you can see that here how the rat paw is moving, that is because you are in the motor area, right. So, fold limb movement in anesthetized rat during intracortical stimulation of specific motor cortex regions on left and right hemisphere using a tungsten wire with an in-house developed stimulator. Again, see that this movement here, right, that is because of the electrical signal that is provided to rat's brain, alright. That is how it is. And let us go to the next slide. So, this is how the experiments are done. This is the in vivo experiment or recording in an awake rat. You can see the rat which is awake, right, here, and electrical signals stimulation can be given here. This is a wired version. As you can see that wires are coming on the rat's brain. The wireless version is better than wired version because it will allow the rat to freely move on the treadmill or a catwalk system. Right now, it is all about how long the rat can be alive, right, without causing any kind of infections, and whether we are faithfully able to record the signals from all the channels. So, we were able to do that. You can see that local field potentials during the moment is very clearly observed when we go from 0 to 10 seconds. The y axis is 80 microvolts and the x axis is for 1 second. For here it is for this is the one that I am talking about. Here the recording is done for 10 seconds and number of electrodes are 10, 5 on each side. So, the overview, again if you see that there is a wide angle camera, there is a rat with a backpack that will move on the catwalk system. We have interfacing PCB with casing, electronic system with casing connected as a backpack, and the remaining things we have already discussed. This is a complete system developed in house in the Department of Electronic System Engineering, which is my department, and in the lab which is in the ground floor, that is exclusive for developing this system. Okay. And then all the experiments we need to perform in central animal facility of the institute. So, when you do that you need to also understand and review what are the literatures. Very important to first review the literatures and then only start your work. So, when you do the review of literature, then you will actually understand what are the existing microengineered devices for surface and deep brain animal studies, and based on that you can optimize your design or use the current design so that your time can be saved. So, this is all about the micro electrode array stimulation in the rat's brain for the Parkinson disease. Now, you do understand that in spite of our best effort, right, the syllabus that you see and the syllabus that you that I was able to cover it is little bit different. The reason is that we have covered 70 or 80% of the syllabus what was shown it to as a week 1 to 12, whether you talk about the microengineered arrays, fabrication of thin film deposition techniques, techniques for acquiring neurological signals, characterization, MEA for neuro potentials, flexible MEA fabrication, deep brain stimulation, what are the needs, right, system using 3D printing, non-invasive BCI which is for recording the data from the neonates, recent trends in brain computer interfaces, epilepsy basics, basics of EEG, approaches for seizure detection and what not. That some of the introduction also we have discussed about how the brain 1020 system, right, how the anatomy of brain, whether it is a nesion or inion, how the electrodes are placed, this comes in the introduction basics. Some things we were not able to cover was computational neurobiology for modeling cells, functions and local networks, complex networks and specific cases, and large scale network and optimization. These things were we were planning and in fact Dr. Vikas was going to talk more on those subjects if the time permitted, but because of his ill health he is not able to do that. So, what I will do is, even we have crossed more than 30 hours as a part of this particular course, I will try to cover some of the topics that we have proposed in week 1, 2, 3, 4 as 1.5 hour of the class, so that we can at least know what are the different computational techniques, right, that can be used for this particular application, whether it is your modeling of cell functions or complex networks or large scale networks and optimization. So, I am really sorry, the reason is not to keep on talking on one technology, but the reason is to try to explain using this online mode in depth, so that tomorrow when you take this course, right, it should be fruitful. You should be able to understand how the fabrication is done. When you understand how the fabrication is done, then you can understand, because you see the computational neurobiology techniques you can always read. Of course, it is very difficult, right, it is not so easy topic to pick up and read, but before you understand neurobiology and all these things, right, if you also understand the fabrication and implantation and the acquisition and the stimulation, that becomes very interesting actually from both Vikas and my point of view, and that is how a little bit of not dot by dot comparing what we propose and what we are teaching, right, but like I said, almost 75 to 80% is taught with best of our efforts, and you do understand that we wanted you to look at the experiments, right. The experimental laboratories are very difficult for most of the students that I have been teaching in last several years through this particular platform. Most of the students does not have or do not have the access to the laboratory facilities. So, that is why I spent lot of time on recording those experimental labs, so that you have some flavor of understanding how the things are done. It is very difficult if you really see that to record the experiments and to try to replicate those experiments through the online mode is not so easy, right. So, with our best efforts we want to cover as many topics as possible within the 30 years of time frame. However, since some of you may have a question about what should be there in that computational neurobiology, right, I will take about an hour and a half depending on the time, so just go through these topics, so that we can cover the course. Again, both sincere apologies from Dr. Vikas, and just conveying it to you because of the issues. He was not able to cover some of the topics and not able to participate, but he is there, he is advising us on all the topics, he is helping us with the assignment, he is helping us with the neurosurgery part, and also helping us with the implantation part, how the design should be there, how the electrodes are there, and that is how I can teach you that part of the course, right, because without neurosurgeon telling where exactly to implant, what to implant, where the needle should go, engineer cannot teach you. So, that is the reason. So, but if you have any question about understanding in detail, please feel free to contact me. Also the assignments sometimes that we give it to you all does not have to be just exactly topic wise. I also want to do little bit of homework and see what are the different applications, right. If you understand lithography, what kind of different photoregists are there. Suppose I teach you UV lithography and I ask you on E-beam lithography, that does not mean that exactly topic should match. I want you to explore and learn something beyond what we are teaching in this particular course. But as far as the exam is concerned, exam would cover the thought process by yourself, the efforts that you do, and the course and syllabus and topics that we have covered in this particular class. So, but still if you are confused, feel free to contact me and I will spend time to clear your doubts if it is not clear through the 30 hours of our coursework. In fact 31 hours, because 1 hour I will be taking in the next as a part of the next remaining topics of this course, right. So, till then I hope that you are gaining something, you are learning something, it is useful, it is advanced enough for you to talk as advanced neural science for engineers. If you have any questions, feel free, guys. This is not so easy topic to digest and to do it. The fabrication part that I am showing it to you today, I am working in this area from last almost 15 years or close to 15 years as a part of my master's program or PhD program or postdoctorate program, or last 6 years of my life here as a faculty in the institute. So, after that it becomes slowly and gradually easier for you to understand how to fabricate it, how the device will look like, what should be the thickness, what kind of simulation you can do, but try to understand it, right? Try to understand it, grasp it, and there will be doubts and there will be questions that we are supposed to answer as much as we can, and that is why your NPTEL platform is there, the forum. Please keep on asking and be curious, right. I wish you all the best for the remaining class, remaining time. Any questions, shoot me an email, right, and I will see you next class. Take care.